Hello, everyone. I am recording this clip to help you to review as I promised. This semester we started with reviewing contents from previous courses, which are including pre-calculus, trigonometry, college algebra, and all the elementary algebra, intermediate algebra, pre-algebra contents. But we only had, I think we merely had like a little over 1 week to review. So as you can see, there are lessons from the past that in the preparatory materials that are available as you need them for you to review. So here in Canvas on week number 1, and you can see all of these contents. But of course, I don't expect you to review all of them, but it's whatever you need, just pick it up. And there was a quiz and solution to the quiz that's available. And so if you have any questions, please feel free. Second week, we also reviewed, we reviewed for 2 weeks, I think. Yeah, but it's because we have a one day that was one Monday that was not a school day. So that's just 3 lessons we reviewed. So quiz number 1, quiz number 2, and primarily on some quiz number 2 and quiz number 1 basically are on techniques, algebraic techniques such as rationalizing numerator and simplify complex fractions and so on and so forth. So these sort of techniques. And on week 3, we have these posting, but we have started lesson. We have started introducing limits. So here I'm going to, if you look at the flashcards, I'm fast forwarding, right? So mathematical principles, we have reviewed, and then we get to the first topics of our calculus class, limits. Limits. As we said, the definition of limit is very, very important. So I put the limit definition right here on the flashcards right here. And we know that in the definition of limit, the function is defined on some open interval that contains A, except possibly at A itself. So the limit definition does not require the function has to be defined at the point. Okay, so let me write it down over here. So limit as x approaching A, f of x equals to a constant, a finite number. So if this exists, right, this of course is an intuitive definition of limit. And so in this limit is read as limit of f of x at A. Okay, so it's read as limit of f of x, which is a function, at A. Okay, and since it is not have to, the function does not have to be defined at A, therefore, there are many situations. There are many situations. So in our homework, you will see the variety of situations that apply that. But when we are doing our homework, right, we want you to be aware of all these concepts on the flashcards that are related to the homework, because that's the practice we want you to practice. For example, homework number 3, right? Homework number 3 on limits. You see, these are the algebraic expression we have practiced, and these are the limits, right? We want you to find those limits. And in situations, you can see h approaching 0, but this function here is not defined as 0. So you can see, I want you to relate that to the definition of limit, right? On this piece, on number 2, you can see when u is approaching 2, but this function is not defined at 2. And the same goes with many limit in our considerations and so on and so forth. And of course, they're graphic, right? And also we introduced sided limit, right? So we have intuitive definition of limit, and there's some notes there. And here we have introduced a direct substitution property, which says if f is a polynomial or rational function and a is in the domain, this is the property we used a lot. So if it is in the domain, then we can direct substitute. And later, of course, we have learned continuity. And we know that polynomial and rational functions, they are all continuous in the domain. Of course, we can directly substitute, right? So we're making connections with what we learned afterwards, and we did learn, right? And the one-sided limit is when x is approaching a from left or right. So the other notation, okay, so x is approaching a from left. Okay, I need to see the font. So hopefully, I think you can see that, right? The limit from left and limit from right. Okay, so we use these notations to indicate when we approach a from different directions. One is from smaller and the other one is from larger. Okay, so in our homework, as we introduce sided limits, and we want you to be able to use them, and we have a very important theorem. This important theorem was used over and over again, right? In many situations. So when you review your homework, I wish you to always think of this theorem to make statements here. Okay, so actually I'm going to type this theorem right here because it is, I'm going to probably quote later on, okay? If and only if, right? So if that is true, right? So the arrows in both directions. So this limit from left is going to be the same as limit from right. If you think about how many questions we've done in relationship with these, right? So you will make sure when you do these homeworks, you relate these concepts. Okay, primarily this theorem is the guidance. It's a guidance for us to make those statements. So limit from left or limit from right to determine if limit exists. We've done all of these examples in class. Okay. So these are the graphic situation, or you're given piecewise function. So we're given piecewise function, how we find these limits, right? I think we've done this in class, and this example we did in class, and we did this in class. Or on one of those quizzes. Now continue that in some situation that we have to, right? We're asked to find limit, but we have to study the limit from either sides, right? Such as these examples, which we have gone over as well. Okay, so study these, and of course, in the homework in week number 3, I put in some algebraic practice for you to enhance your algebra. Okay, so keep going. These are the concepts, and infinite limit, right? Negative infinity, positive infinity. And of course, we talk about the contradictory nature of this word, right? Infinite limit. Infinite limit should not be put together, but it's in the case when the limit is negative infinity or positive infinity. So we have this, especially related to vertical asymptotes. So this is the vertical asymptote, and this will make a connection to what we have learned before, right? The vertical asymptotes for for some rational functions. And next, limit law. Limit law, we find it very convenient to use, and we use them quite a bit. But we must understand, before we use limit law, we must make sure and we check each individual limit exists. I emphasize this, and I also showed you work in class that how do we show that work, right? You check it, and then you reflect that in your steps. You reflect that in our steps. So this will come to, you review the homework in week number 3, and then you realize, I cannot use a limit law here because the individual limit does not exist. We have to operate, right? We have to operate them as one entity and reduce it, rationalize it, because we cannot apply limit law here. That's what I wish you to understand. Okay? Now, the next one, of course, the next flashcard is a continuation of limit law. And another theorem. Okay, this theorem is also used a lot, so I wish you guys to be aware of it. For example, one of these questions, right, after we reduce them, we will be able to use this theorem. So this theorem was also used a lot. And of course, this is the repeats, right? The same theorem on sided limits. The next one is saying if, okay, let me make it larger. If one function is smaller than or equal to the other, and we take limits, and they still have the same relationship. So this will lead us to squeeze theorem. Okay, so that will be taking us to week number 4. Okay, so in week number 4, we have exercises about finding infinite limits, right? In some cases, these are primarily is about the vertical asymptotes. Okay, if you relate to that definition, feel free to graph them when you do the homework, and of course you also need to interpret it from the definition perspective. But regarding squeeze theorem, as I said, it's always tested, right? So we have 7 questions, so we've done most of them. So hopefully you guys, and we also have a quiz due, right? And I'm going to point out some exercises that and other recordings about this. And once again, we give you homework about finding these limits, and these limits, right? Most of them we cannot do limit law. And you need to do some reducing algebraic manipulation before we can use limit law in some cases. Number 4 here, you see it's very typical. You have to consider limit from left or from right, right? So these are the exercises. They are focused on the concept. They're focused on the concept. Okay. And evaluation, for example, on number 11 here, can we evaluate this? Sure, because soon we have squeeze theorem, and we also have continuity. Okay, we have some nice theorems I wish to point out. The definition of continuous function at a point, and then afterwards, right? So we have left limit, right limit, these definitions there, and how, what the definition of continuous on an interval. And then we got some difference of a product and a constant multiply function, quotient of functions of continuous functions, they're all continuous. And there are other very, useful theorem that we use all the time is, we already mentioned this earlier, is polynomial and rational functions. They're all continuous in their domain. And what is more, besides polynomial rational functions, they're all continuous in their domain. We have root function, trig function, the arcsine, arccosine, arctangent functions, exponential functions, logarithm functions. This pretty much includes all of the functions we have learned in algebra classes. Okay, and the next theorem, this theorem is that saying that if we compose these functions, we also have continuous function. So that's also very, very powerful, and we use it a lot. Let's look at the next one. Yeah, this one is in general, right? If f is continuous and G satisfies certain conditions, and G is continuous and f is continuous, the composition of a continuous function is continuous, right? So that means for all of these functions, you add them, subtract them, multiply them, divide them, composite them, they're always continuous in the domain. So this is a very, very powerful theorem when we combine this one with one. Okay, when we combine these two, they make it very, very powerful. Now, how do we explain these exercises, right? These exercises in homework number 4 is to apply these nice theorems, right? For example, in the case of number 11, right? Number 11, it says evaluate limit as x approaching pi sine x over 2 plus cosine x. Okay, I'm going to write this question down, and I'm going to write the answers to you. See how I put the narrative together. Because when we are doing these questions, we're not just plugging numbers. Sometimes we need to say something. We need to say something. Okay, so over here, I'm going to borrow this notation. And I'm going to take this question per se, right? Which is it says find the limit, right? And x approaching pi. And we have a specific function here. And this function goes like sine x over 2 plus cosine x. How do I use all these things we just went over? Right? Find the limit. It says find the limit. Find the limit. How do I make use of what, all of these nice results? Well, in this function, we have sine function, cosine function, and basically we have one function, another function, plus another function, plus, cosine function. We have 3 functions, you can see that. But we said adding, subtracting, multiplying, dividing, the whole function after all of these operations is going to be continuous in the domain. So our next question is, what is the domain, right? Well, we can go about to say the domain of this function, or the domain of sine is all real numbers. Domain of cosine is all real numbers by themselves. But this specific function, domain of this function, we need to guarantee that 2 plus cosine x should not be 0. Okay, that should not be 0. Can that be guaranteed? Do we have some numbers we need to exclude? Well, cosine function is between -1 to +1. So with that knowledge, which we are familiar with, the domain of this function, this is guaranteed. This is any real number. Any real number, right? The domain of this function is all real numbers. That is, domain is all real numbers. All real numbers. If domain is all real numbers, then we're going to quote that theorem, right? So by the theorems, right? And this is the division of two continuous functions in their domain. So this entire function is continuous. By the theorems, this guy is continuous everywhere. And if it's continuous everywhere, certainly it is continuous at pi. And so we can directly substitute. So we need to say something, explain why we can directly substitute. So what do we say here is that we're quoting the theorem. We're quoting the theorem. So then we have sine pi and 2 plus cosine pi. Right, sine pi is 0, so the whole thing is 0. So the substitution part is easy. I'm sure everybody can do it, but I want you to think from the perspective of our contents, So all of these questions, a lot of them are in a similar situation. Okay, so here, like it's 9, 10, 11, 12, right? And number 13, questions like these is where the following function continues. You basically need to determine the domain. For A, it's all real numbers, right? For G, 1 plus sine x has to be positive, has to be greater than 0. I think we did this in class. So if you still have questions, please let me know. Okay, so that's about continuity. And next, what is the relationship between continuous function and the function has a limit at A, right? So for function has a limit, for limit, right? That's the function has a limit. And we mentioned that where f is defined near A, except possibly at A. Oops. Okay. We compare these two definitions, right? So what is the definition of continuous at A? Continuous at A, right? So we compare these two definitions. So limit at A, compare with function continuous at A. Continuous at A, we need to have limit. We need to have 3 items, right? We need to have 3 items. So this limit exists and it also equals to f of A, right? There's 3 items. So the continuity definition is stronger than limit. Therefore, if we know a function is continuous at A, right? If a function is continuous at A, at A, oops, at A, right? Then limit exists. So then the limit exists. So continuity is a stronger condition than having limit. Now, keep going. We in week number three, right? We have some limits, one-sided limit examples, and these lessons you can take a you can if you need it, you take a watch it. And all of these is about limits. All of these and a lot of them, about their homework, about squeeze theorem, how to apply squeeze theorem, absolute value, and one-sided limit. I made a special session for it, so hopefully that will help you. Week number 5, besides the class, the lectures in class, we also have continuous functions. I went over those limits with the examples. Intermediate value theorem. Intermediate value theorem is a must tested content. So we have that, and we also quiz you once, right? So intermediate value theorem, I prepared 2 recorded lessons on how to say it, right? And the quiz, and week number 6, and by this time we have introduced differentiability, derivative, right? Limit at infinity, we have 2 of them, and then we introduce differentiability. With differentiability, by definition, and there was a midterm review that was done with more examples. That was a recorded lesson. You guys can take a look. I'm going to take a look at this review for midterm before I publish. There are some more exercises for you to do. These are actually from the textbook. I think you do your homework, that will be enough. Okay, so I'm not going to add more work for you. Just your homework is enough. So I'm not going to publish this. And if you want to have more exercise, you can go to the textbook to find some questions to work on. And the next one is differentiability, right? So let's go down the okay, we introduced differentiability. So these are still continuity, so derivative. On derivative, right? So we have some recordings already available, right? And we also have a definition. Which definition will be used the most? Well, I can tell you, on the exam, I would have you use this definition to find derivative of function at a number, and also I will have you use this other definition, which is to find derivative function. This definition is to find derivative functions. Okay, so let me put it side by side. Okay. Limit as h approaching 0. Maybe I can make the fonts larger. To 300%. Okay, 300%. Okay. So f of a plus h minus f of a divided by h. And the other definition, so I'm going to make a table actually. Let me make a table with one more row, right? So this definition is for, of course, if this limit exists, right? This is to find the derivative of a function at a point or at a specific point, right? So it's also the slope. This case is the slope. It is also the slope of a tangent line at a point. This point is a f of a. We had some exercises done in class, right? So this is a find derivative at a point. And this other one, which is the x plus a turning into x, this is to find derivative function. This is to find derivative function in general. So the derivative function, of course, include they give you the slope of all the points that is differentiable, right? So this is find derivative function. I think this is just a little bit too big, 250%. Okay, there we go. So this is find derivative function. This is to find, so suppose it's differentiable. Suppose it is differentiable, then that's how to find derivative function. And feel free to use notation such as dy over dx. Okay. Regarding derivative, we have learned, in last lessons, we have learned, the derivative of sum is the sum of derivatives. The derivative of difference is the difference of derivative. We have proved those theorems, and those can be used when you find it applicable, when you do homework, because that's something we're going to use for homework in week number 8, which is next week. I wish you guys get started on reviewing, right? And the next topics I like to address at the end of this recording is what is the relationship between all three concepts, right? All three concepts. So I'm going to put it together on a table, right? Limit at a. Limit at a, okay? And this sentence is very important. F is defined near a except possibly at a. Okay, so let me add another column. There we go. So we put that in there. Well, this is the disadvantage of this software. So bear with me. So this is defined near a except possibly, I'll have to reduce it 175%. Okay, except possibly at a. Okay, so that's going to be red. Is defined at near a except possibly at a. Okay, I hope this is clear. All right, so in comparison, right? Continuous at a. Continuous at a. Continuous at a. Limit at a. Right, so we make it a little bit more compact. Limit at a. Differentiable at a. Differentiable at a. at A. Differentiable at A, of course, that limit exists, right? This limit exists. Okay, so all of these exist. Now, which one is stronger? We have a very important theorem I wish to mention, is that we prove that in class is that differentiability guarantees continuity. So I'm gonna point it out which theorem is that. Let me find it. It's somewhere. There. This theorem. If f is differentiable at A, then it's continuous at A. Okay, so what's the relationship between these three? The relationship between these three is that hold on. There we go. So I'm going to put it this way. Okay. Differentiability guarantees continuity at A. Guarantee continuity at A. Continuity at A. And continuity at A guarantees limit at A. Limit at A. Okay, so how do we do that? We do that by comparing the theorem, comparing the definition, but not the other way around. Not the other way around. Say, for example, we have examples that, so if I ask you, if limit does not exist, can this function be continuous at A? Then you say it's not possible, right? So differentiability guarantees continuity, continuity guarantees limit, but the other way around does not work. And you need to know counterexamples, okay? Some counterexamples, some examples, right? Some examples illustrate that. One of the examples we did in class is that f of x is equal to absolute value of x, right? Absolute value of x. And it is what? It is a continuous at 0, but not differentiable at 0. Okay, so this is a very important example. And the limit exists but not continuous. For that case, we have many, many examples. You just look at the homework we did, then we will, we have many, many examples. But all in all, I wish you guys, when you review the material, you still have the flashcard with you, you review the work you have done, you have the flashcard with you, and you refer to each step, what have been used from the contents of calculus. And that's how I encourage you to study using that method. So in the end, you'll be very familiar with all the theorems and when to use it Okay, I try to not make it too long. And I hope this will be an introduction for you, for your review. But if you have any questions, please don't hesitate to bring it forward. Thank you for watching.